Hey, so today I'm going to talk to you about a subject that I haven't talked about on this channel actually for a long time now, which is logic encoding and utilizing different languages and programming languages to code logic and within programming languages. And so this has been something that has fascinated people since the 1960s. One of the languages that I'll go in here, Prolog, was created in the 1960s, and it's like kind of the first attempt at this. And then so Prolog utilizes facts, rules, and queries. And then so facts represent basic relationships, like parent. Rules represent logical conditions, like ancestor, and then queries process logical-based queries using an inference engine. And then so if we look at kind of how Prolog works out, and what it does is it takes like logical statements, right? Is John the parent of Mary? True in this instance, because we're coding it out, and I'll show you. And then is Mary the ancestor of Susan? And that's true in this instance, right? And then so we're encoding like John is the parent of Mary, Mary is the parent of Susan, Susan is the parent of Peter. And then pretend like this is your data that you have within a database or anything like that, right? And then it has to be structured very logically and as a logical database, right? And then so you structure your logical database, and then in this instance, I'm converting it to NumPy arrays, and so I'm doing everything that you would do in modern terms. I'm just utilizing Prolog, and then Prolog in this instance, the limitation is it's only for logic, right? This is very good for logic, and you have to create the logical database, your steps, and additional work. If you want to do things like arithmetic or other types of like inductive reasoning, it's not going to do it. It has to be structured logic in this instance, right? And so that's Prolog. And then so we have other examples of this. So that's the limitation, right? So people took these limitations and they tried to go forward, right, with it. And then so it encodes basic logic, but there's a lot more logical functions that you could encode, right? So the next example that we'll look at here is called higher order logic. And so higher order logic encodes higher order predicates. So for all exists, implies, lambda, and it runs off of those. So it gives you more data than when we get with Prolog. And then we can also map variables and entities to structured numerical representations. And we can train a neural network on these things. And then so we go through, and then it's the same types of mappings and relationships, right? So, but then in this instance, we structure it differently. So we have entities, and then so we would have John, Mary, Susan, Peter, and Kate. And then we have relationships, so parent, ancestor, sibling, and grandparent. And then we have higher order maps, right? So for all exists, implies, and lambdas, our join functions, in the different ways to join the relationships. And then again, the same data. John is the parent of Mary, Mary is the parent of Susan, and Susan is the parent of Peter. And then same thing, is John the parent of Mary equals true, and does there exist an ancestor of Peter equals true? And then so in this instance, what higher order logic allows us to do as opposed to Prolog is one, we can fully train a neural network off of these encodings. It's just easier to translate higher order logic encodings. So I've done it here, and I'm just using a standard neural network, ReLU with Atom, and training it. Very straightforward, right? And then overall, higher order logic has the same problems with Prolog, which is that it's a logic-based, but simple logic-based and not arithmetic-based at any level, right? And then so we get into the next example of this, which is a first-order predicate calculus. And then first-order predicate calculus is kind of trying to be a more advanced higher-order logic, and then it takes arithmetic into some account within this, right? So it encodes logical facts and rules with quantifiers, and is kind of the big difference. Also uses structured and numerical representations. And so in this instance, we go through, and then we do our facts, and then we get our arithmetic calculation out of this, right? Our logical calculation out of this. But the bottom, when it comes to all of these models, they're all built around logical reasoning. All three of these that I presented, Prolog, first order predicate calculus, and higher order logic are all designed to increase logical reasoning, deductive reasoning within the model. And then so that's kind of the breakdown of how these systems work. And then within that, we want to arithmetic is its own separate entity from this, right? And then that's a known problem that exists, is how exactly do we incorporate arithmetic into these things. Like all of these languages that I outlined, they don't do that. And someone, the reason why I'm doing this is one of my followers, they shared a notebook with me, and they are essentially a chat that they were having with ChatGPT, where they invented this hierarchical relationship encoding language, and then their end language is very specifically like the opposite of these three that I just showed you. Right? I showed you these three languages are all for logical predicates. Whereas this language that I'm going to show you is all for arithmetic. And it's arithmetic and algebraic relationships, and they're nested, and they're as nested structures, right? So it's a really cool breakdown. It like linearly codes logical relationships or arithmetic relationships. The problem with this is it's not encoding logical relationships, and that's why I showed those three up front, right? So I'm going to show you this model, and there's so we have three examples of models that are encoding logic and pure logic, and then this example, which is coding pure arithmetic, right? And this is the first good example of a high level example of this that I've seen. There's not, I wouldn't say it's the first example period that I've seen of coding arithmetic in this way, but it's this is a really good high level method on how to do it overall. And so you take your operations, right? And you're essentially just encoding your operations as a binary. And then so you can see 1 0 0 0 0 1 0 0 0 0 1 0 and then 0 0 0 1. And then those are for plus, minus, multiplication, and division, right? and so we're just straight up, flat out encoding them into binary. So these become tokens for the model. So if the model wants to do minus, it's 1 0 0 0, and it's completely logical to the model. And then on top of that, we're encoding the logical relationships and the operations. So and, or, XOR, and not. And then we code in our variables, so X, Y, and Z. And then in this instance, we go through and I train the model. It's a lot of code here for this, but we're training the model essentially to predict true-false statements on this. So more like arithmetic, right? Is this equation true or false? And then I run on this particular test, I run through arithmetic, logic, and algebra to show you the different tests that we can see. And then so on arithmetic, that's what this model does, right? It's getting 60% accuracy with base training, but on the logic, it's guessing 33% accuracy. And the only reason why it's getting 33% is it's just guessing true every single time for the logic, and then true happened to be true 33% of the time. So it would probably be closer to 0, right? Because it's just guessing true all the time. And then algebra, the algebra mean square error, same exact issue there. Essentially, the model isn't reasoning from this or abstracting from this very well. This is a very good method for arithmetic solving, just like these methods are a very good method for logic solving, right? And then so we can see we have at this point two disparate methods, and so this method that the user showed me is super cool with regards towards solving the arithmetic problem within this, right? There's kind of a gap that exists within these other languages, these three that I showed you, specifically with arithmetic. And then so I create, in this instance, as the end result, the universal logic encoding neural network. So I'm incorporating both methods, right? The arithmetic encoding and the logic encoding, which is cool. I haven't seen it this specifically done before, so thank you. And then here's the end result, right? And I do a whole bunch of tests for here, and I'm essentially just testing it on different things, and then you can see so this is a small neural network, and then this is a simple test, my first test, right? But so the testing comes out pretty good as far as what I would expect, and so we can see the known facts is John the parent of Mary. It can get that. Is Mary the parent of Susan? It's very good at these, right? All of these are correct. Is Peter the parent of Susan? It said true. Is John the parent of Kate? It said false. And then so it only got 2 out of 10, and so I got 80% accuracy on that first one, which is high, right? And then arithmetic, got that right, wrong, right, wrong, right, wrong. So it got 7 out of 12 on arithmetic. And then when we tested on brand new examples outside of its data set, this is what this is. So for that first test, the logical reasoning test, it was true, true, false, false, true, false, false, true. So more it drops to 55% accuracy essentially when we move over to testing off of like away from the data set, but this is good though. Like this is something as far as generalization. And then same thing with our like actually kind of worse with the algebraic equations. It ends up getting 2 wrong and 2 right in this instance on that test. So and then it's like again like 50%, 50% accuracy is what it hovers around there. So overall, this is super cool. Like the general accuracy of this model overall is the training accuracy is 71%. And then so again, this is like the first test, very small model utilizing simple logic and arithmetic on this small model. So you can get much higher than 71% accuracy on these things, right? But so just highlighting overall within this, like I have a ton of experience with like this logic encoding. This is actually like kind of my first love when it comes to AI, right? When I first started like trying to like reverse engineer and take all of it apart, this is like the very first place that I focused on was the word embeddings themselves and the way that models embed words. I thought if we can just fix this process, we'd get a lot further, right? And then so I invented a method called PFAF, probabilistic fractal activation function. And then it's interesting because I don't know why, but I go to my GitHub and I had like a whole bunch of repositories here around PFAF, and for some reason they're gone. But I have in literal court proceedings, I stamped my authorship over PFAF. So if I ever have to sue anyone for authorship over this, it's in court documents already. But so within this is the probabilistic fractal activation function, or PFAF, and then essentially. So all of these methods, right? These are all encoding the utilizing like the training data and trying to encode a method for linearly doing these things and giving that to the model, right? And then essentially like here's a framework for you to use, and then like and it's going to be very linear. Whereas so PFAF, what PFAF does is it's very simple. So if you go to my Hugging Face and then you go to my Hugging Face specifically, and then my data sets, if you expand here, this is other proof of ownership and authorship, right? So PFAF and PFAF2, PFAF3, PFAF 750. And so this one, PFAF 750, is January 17th, 2024. So over a year ago now that this is here, and it hasn't been changed. It's the last time it was updated, right? And then, so this gives you like, what is the PFAF function? Can you explain the PFAF function in other words, etc.? But so essentially what this method is I took what was thought to be an unsolvable equation within geometry. I converted it into calculus, created the PFAF function based off of that, and I created this testing data set of 750 samples and rows in order to teach the model how to utilize this probabilistic fractal activation function, which essentially is what this is, but I turned it into a training data set, and I said, hey, let's, instead of like making this 100% linear, which is all the problems within this, right? It's you're breaking it down so that it's all using linear algebra, which is straightforward, and I understand that, but I wanted to use geometry and calculus in this instance, and then so I started with geometry first, and then that's where I ran into the unsolvable equation problem, so I converted it into calculus, not being a mathematician, not knowing that it was unsolvable. And then so went through and created this, and then so essentially what this is like this is the exact equation here. And then, so what it does is it allows like the model weights. So you have the model like X, PI, FI, and DI, and then these are representative of the model weights. And then this teaches the model how to utilize its weights probabilistically, how to literally create probabilistic math utilizing its own weights. And then my like assumption and my thinking at this time was like this. I was on the track of like how exactly are these models learning, right? And so you can see a year and a half ago is when I started thinking like these models are learning probabilistically. They're utilizing, I don't know what it is, like shape. I had no idea that like shape was a huge part of this equation at this time, right? But I knew that geometry was. And then so I was trying to figure it out. And then so I was like, well, like every like all of these approaches, like every single one of these language approaches is linear, and they're all based in algebra. Let's base it in probabilistic functions, and so that's exactly what I do here. I create the data set, I train the models on it, And then across the board, what ends up happening is if you measure, so if you take this PFAF 750 data set, and if you take your base model, you're going to increase your GSM-8K scores, which is your logical reasoning scores of your model, by about 5 to 6% on average, just from this 750 row data set. Literally just fine-tune your model on this data set here, PFAF 750, and I guarantee you, you are going to increase the GSM-8K score of your model. Plain and simple. I just got tired of explaining this to people. It's hard math to understand overall. So PFAF is out there and available to the world. Obviously, somebody doesn't like it because they did something. I don't know what's going on with my GitHub here as far as PFAF. There's one repository here, but there used to be more. Again, it's all court documented on my end, so I don't care on that end. But so. Overall, I'll leave you a link to this description and this notebook for logic encoding in code languages and models. And then so if you like this type of content, please like and subscribe. Thank you very much.